Okay, guys, I've had a few of my students ask me to refresh them on what linear dependence is and independence. Um, so we're going to quickly run through it in both the two-dimensional and three-dimensional planes. So, um, linear dependence, linear independence. If I've got two vectors and they're in a plane, um, just say I had a vector that was like, oops, that didn't work. So there's A. And I've got a vector B, which is a different length, but goes in exactly the same direction. If we can say that we can multiply A by some factor to get B, like a scalar factor, just a number, in this case maybe it might be B is equal to 1/2 of A, then we can say that they're linearly dependent. So when it's a two-dimensional vector, we've got two-dimensional vectors in a two-dimensional plane, then they'll only ever be linearly dependent if one is a scalar multiple of another, i.e. they're collinear. Actually, they don't have to be collinear. They will be collinear if they share a point. But if they don't share a point, they will be linearly dependent, basically, if they have the same gradient. So if I have a gradient like that and a gradient like that, the gradient will be exactly the same. It doesn't matter about direction because the gradient will be positive in this case or negative in this case, but one will be able to be multiplied by a scalar factor to get the other one. So that's what linear dependence is. With two vectors in a two-dimensional plane, they will only be linearly dependent if one is a scalar multiple of the other, i.e. one can be multiplied by some scalar factor, some number, to get the other vector. So I've said here, if they can't be expressed as a scalar multiple of each other, they're said to be linearly independent, i.e. they don't exist going in the same direction. Okay, if I have three vectors and they're not parallel in a two-dimensional plane, so this is the significance here, in a two-dimensional plane, if I had three non-parallel vectors, so if I had one going this way, one going this way, and another one like this, they're said to be linearly dependent because two of the vectors, if I just use two of the vectors, so if I use this vector here, and I use this vector here, I can span the whole plane, right? I can span every single position in the plane. If I wanted to make this vector, this one here, I could say 2/3 of this one, so 2/3 of that one, and then plus 3 on 2 of that one. Together, when I add those two vectors together, I can make up this third vector. So in a two-dimensional plane, if you've got three vectors that are not parallel, then those vectors are always going to span the whole plane. Okay, so if they span the whole plane, then they're all linearly dependent. If I had two parallel vectors and a non-parallel vector, there's no way with these two vectors that I could make this vector, because if I add one to the other, there's no way I'm going to change direction and make this vector. The only way that these two could make this is if this was a zero vector, because that would have to have no length, and if it had no length, then I could make that is a scalar multiple of that, like some scalar factor to multiply this vector to give this one. But as a set of vectors, they wouldn't be linearly dependent. Okay, so that's three non-parallel vectors. They're linearly dependent if you can express them as scalar multiples of 2, add them together. If they can equal the third vector, then they they will be linearly dependent. So two vectors, if you've got three vectors and none of them are parallel, with those two vectors I can span the whole plane. Like the two-dimensional plane, I can make up any vector by adding them together. Likewise, if I use these two, I can do the same, and if I use these two, I can do the same. So they will be linearly dependent. If they can't span the whole plane, then they're linearly independent. Okay, when we have three non-parallel vectors in a two-dimensional plane, they will always be linearly dependent, as one vector will always be able to be expressed as a sum of scalar multiples of the other two, which is what I just said. In 3 dimensions, three non-parallel vectors are linearly independent, unless there exists an M and N such that A equals MB plus NC, M and N can't equal 0. If there exists an M and N that satisfies this equation, the vectors A, B, and C are linearly dependent. Now, basically what that means is if I had a three-dimensional plane and I created X, Y, Z, if I had a vector X and a vector Y, so we'll say this is I, J, and K. Now, if you look at these three vectors, they're linearly independent because there's no way that I could, like, they don't all lie in the same plane. So I can't use the multiple of these two vectors to get this one because it's going in a completely different direction. So if they did lie in the same plane, then they would be linearly dependent. But because they all lie in different planes, and I can't use the addition of the scalar multiple of two of them to make the third one, there's no way that they are linearly dependent. So if they were linearly dependent, they would all exist in the same plane. Now, what I mean by that is if I had a three-dimensional space, now I'm going to tell you that I've got a plane, like basically if you think about it, I've got a piece of paper that's sitting in 3 dimensions. Right, so there's the piece of paper that's sitting in between the axis, that's behind it, that one, it's in front of it. Yeah, it'll be in front of it. So here, okay, and it's in front of that one. Okay, so there's my piece of paper in a plane. It's just a flat piece of paper in a three-dimensional plane. Now, if I had three vectors that lie on that piece of paper, so there's one, and there's one, and let's say here's one. Now, well, what did I just do? Those vectors, because they all lie in the same flat plane, they're called linearly dependent, because I can use these two to add together to make this one, or I can use these two to add together to make this one. If I make scalar multiples of them, these two can make that one, because they all lie in the same flat plane. If one of them didn't lie in that plane, then I couldn't span this whole plane, this whole flat plane, so therefore they're linearly independent. So they all need to lie in the same plane for them to be linearly dependent. And the way that you would test it is if I made these two vectors, probably can't really see them anymore, let's make it green. If I made these two vectors, if I said, does there exist some value that I can multiply this vector? So if I said A times M, so M is the scalar value, A is a vector, and then B times N is the scalar value, B is a vector. Can I multiply, add these two things together and somehow make this third vector C? If I can, then they're linearly dependent because they lie on the same plane. If I can't, then they're linearly independent because they don't lie in the same plane. So you could use this to see whether planes are going to crash or something like that, to see whether they lie in the same plane. If they don't lie in the same plane, then they're not going to hit each other, making the assumption that the plane's like a particle, like a small, really small thing. Okay, so here, I want to see if these vectors are linearly dependent or not. Now, this one you can do by inspection, just by looking at it. This one's got a gradient of 2. No, ij. It's got a gradient of a half. This one's got a gradient of negative a third, and this one's got a gradient of 6/5. So we know these are going to be linearly dependent because none of them are parallel. But let's do it the mathematical way. So 2, we'll say AM plus BN equals C. Does there exist a value of m and n such that we can satisfy this equation? 2m plus 3n is equal to 5. The second one, I'm going to double everything just to make it easier to subtract. 2m minus 2n is equal to 12. Equation 1, equation 2. Now, if we do 1 take away 2, I'm going to get 5n is equal to negative 7. So n is equal to negative 7 on 5. And if we know that n is negative 7 on 5, we know that 2m is equal to 12 minus 14 on 5. What's 12 minus 14 on 5? 60 minus 14 is 46 on 5, divided by 2 is 23 on 5. So what that means, if m was to equal 23 on 5 and n was to equal negative 7 on 5, if I multiplied these values, I would get this vector here, because none of them are parallel, they span the whole three-dimensional plane. So they are linearly dependent. I've got a three-dimensional vector in a three-dimensional plane, obviously. Just realized how stupid that sounded. So let's check and see if I do the same thing. AM plus BN is equal to C. So 3m plus 2n equals negative 1. 4m plus n is equal to 0. Negative m plus 3n is equal to 1. Okay, so we say 1, 2, 3. Which one's the easiest one to work with? Okay, let's do 1 minus 2 times 2. 3 minus 4 minus 8 is minus, sorry, I meant 3 minus 2 times 4, which is 8. So minus 5m. 2n minus 2 times n is 0. Negative 1 minus nothing is negative 1. So I get m is equal to 1/5. Okay, let's use these two equations again, where you need to see if m equals 1/5, what does n equal? So let's put into number 2. 4/5 plus n is equal to 0. So n is equal to negative 4/5. Okay, so that satisfies those two equations. M is 1/5, n is negative 4/5. But does it satisfy the third equation? Because that tells us whether it's linearly dependent or not. So negative m plus 3n is equal to 1. N is negative 4/5. M is 1/5. So if I have negative m, I'm going to have negative 1/5 plus 3 times negative 4/5, negative 12/5. Does that equal 1? No, it doesn't. Therefore, A, B, and C are linearly independent because they don't span the whole they do span the whole three-dimensional plane. So they would make up like the whole three-dimensional plane, but together they don't lie in the same plane in 3 dimensions. So they need to lie in the same plane, i.e. if we put a piece of paper, they need to lie in the same plane for them to be linearly dependent. Okay, so A and B have position vectors A and B respectively relative to the origin. So there's A, there's B. Now what's the significance of this? The point D is such that OD is K times OA. So it's K times A. So OD and OA are linearly dependent because they lie on the same line, or not on the same line, but they go in exactly the same direction. So one is a scalar multiple of the other. Just like with AE, that's a scalar multiple of LAB. So AE is a scalar multiple of AB because there's some L that we can multiply AE by to get LB. So that's what the significance is here. We're saying that OD is a scalar multiple of OA and EA is a scalar multiple of EB. Okay, assume that OX is 2/5 OE, 2/5, so that's 3/5, and XB is 4/5 of DB. XB, that's 4/5, that's 1/5. Okay, find XB in terms of AB and K. Find XB in terms of AB and K. So we know XB is 4/5 DB. I'll make this pen a bit smaller. Okay, so XB is 4/5 DB. And we know that DB is DO plus OB, which is 4/5 negative OD plus OB. Now we know OD is also a scalar multiple of OA, so 4/5 negative K OA plus OB, which is negative 4/5 KA, and then plus 4/5 KB. Okay, sorry, my sister's messaging me from America. All right, so negative 4/5 K plus 4/5 KB, that is what XB is. Express OX in terms of AB and L. Okay, so we know OX was 2/5 OE. Okay, and that is 2/5 of OA plus AE, which is 2/5 of OA plus L AB, which is 2/5 OA plus L. Now AB is AO, or negative OA, plus OB. So we've got 2/5 A minus LA plus LB. So I've got 2/5 A, 1 minus L, plus 2/5 B. Express XB in terms of A, L, and B. It may feel like we're doing stuff for nothing, but eventually we'll see that we can use all of this to find out what L and K are. Okay, so XB is the same as XO plus OB. We know what OX is, so change this to be negative OX plus OB. Negative OX is, so I've got to take the negative of this, so just change that to L minus 1. So 2/5 A, L minus 1, minus 2/5 B, so we had to subtract that 2/5 B, and then plus B. That's right, isn't it? I've got an L here, because there's an L there. So that would be LB. LB and then plus B. So 2/5 A, L minus 1, plus, we can say 2/5 B, L plus 5 on 2, because that would just be 1. Or you could just leave it as B, 1 minus 2/5 L, because that's negative. Okay, find K and L. So we've got XB in terms of K, and then we've got XB in terms of L. So we know negative 4/5 KA has to equal 2/5. Because we've got components in terms of A, and we've got components in terms of B, we just equate the coefficients. So negative 4/5 K is equal to 2/5 L minus 1, and 4/5 K is equal to 1 minus 2 on 5 L. So if we add them together, they will disappear. I've got 2/5 L. What have I just done? I must have stuffed something up somewhere. Because that's just going to give me 0. Not very clever. Oh, that doesn't have a K. Because the K is only with that A, so it's B. Okay, so I think that's much better. So we've got XB is negative 4/5 K A plus 4/5 B. We've got XB is equal to 2/5 1 L minus 1 A, and then plus 1 minus 2/5 L B. Okay, so we know from here 4/5 equals 1 minus 2/5 L. So negative 4/5 is equal to negative 2/5 L. So we know that, oh, I don't know, that's wrong. How did I get that? 4/5 minus 1 is minus 1/5. Okay, so L is going to equal 1/2. And if we know that L equals 1/2, then from here we know that negative 4/5 K is equal to a half minus 1 is negative a half. So 2 on 5 times negative a half. They cancel. So I've got negative 4/5 K is equal to 1/5. And K is equal to a quarter. Is that right? No. My algebra's not too good this morning. Okay. Negative 4/5 K is equal to 2/5 L minus 1, because now it's a half. Okay, so we've got negative 4/5 K is equal to a half minus 1, that's negative a half, so that's negative a fifth. So K equals 1/4. Okay, and we could do that because we knew what was linearly dependent within that diagram. Okay, there's more. Okay, show that the vectors 8, 7, 3, 1, negative 1, 3, and 2, 3, negative 1 are linearly dependent. Okay, so let's do the same. M A plus N B will equal C if there will exist some M and N that satisfies this equation if they are linearly dependent. And that would mean that they lie in the same plane. They're in 3 dimensions, but they lie in the same plane in 3 dimensions. So if I put a piece of paper, they'd all lie in that plane. Okay, so we've got 8M plus N is equal to 2. 7M minus N is equal to 3. 3M plus 3N is equal to negative 1. So let's go with these two because they're going to be the nicest ones. 1, 2, 3. Okay, so if I add them together, 15M is equal to 5 because our n's cancel. M is equal to 3. Okay, so let's put in M equals 3. N is going to equal 8 3s are 24. N is going to equal negative 22. Okay, now does that satisfy? Have I stuffed something up? 8, 1, 2, 7, negative 1, 3. Oh, that plus that. Oh, totally gone, dropped the ball. I'm like, that's not going to work. So M equals 1/3. If M equals 1/3, N is equal to 2 minus 8/3, which is N is equal to negative 2/3. Okay, so we know that satisfies those two equations. If it satisfies this one, then we know that they're linearly dependent. So 3 times 1/3 plus 3 times negative 2/3, does that equal negative 1? 3 minus 2 equals 1 minus 2 equals negative 1. Therefore, A, B, and C are linearly dependent because there was some value m and n that satisfied the equation ma plus nb is equal to c. Okay, show that these are linearly independent. Now if you have a look at this, this, notice the difference is this here. We know that they're going to be linearly independent because it's shot off in a completely different direction, which isn't going to lie in the same plane. But let's prove it. 8m plus n is equal to 2. 7m minus n is equal to 3. And 3m plus 3n is equal to 1. Now when we solve these, we just did it before, m equals 1/3, n equals negative 2/3. So 3 times 1/3 minus plus 3 times negative 2/3 equals 1. Oh, we could just say, what does that equal? Well, we've got 1 minus 2, which is negative 1. Negative 1 does not equal 1. Therefore, they are linearly independent as they do not lie in the same plane. So with this, I couldn't use these two vectors. If I add them together, I couldn't make this third vector because they're not lying in the same plane. If they did lie in the same plane, then I could, but because they don't, I can't. So that's what linearly independent is. And linearly dependent is when they lie in the same plane, and I can use two vectors to make the other vector. So let's just quickly refresh. 3 vectors, 2 vectors, like two-dimensional vectors, and 2 of them in a plane. They will be linearly dependent if one is a scalar multiple of the other. So if I can multiply one by the other, if I can multiply one by a scalar factor and get the other, so they'd have to be parallel. 3 non-parallel vectors in a two-dimensional plane are linearly dependent as long as they're not parallel, because those 3 vectors will be able to span the whole plane, and they'll be able to, one and another, a scalar multiple of each added together will be able to make the third vector. So when we have 3 non-parallel vectors in a two-dimensional plane, they'll always be linearly dependent, as one will always be a scalar factor of the other 2 added together. That's as long as they're not parallel. In 3 dimensions, 3 non-parallel vectors are linearly independent, unless there exists an m, n, such that there's a scalar multiple of both vectors. If I add them together, those 2 vectors, and I can make the third vector, they will all exist in the same plane, so like in a flat sheet of paper in the plane. Hence, that means that they will be linearly dependent. If one of them lies in a different plane to the other 2, then they're linearly independent. Because 2 vectors in a 3-dimensional plane, they can only span, like if I put 2 vectors, so if I put one here and one here, they can only span the piece of paper that lies on both of them. And if you've got another vector which shoots off in a different direction, which doesn't lie in that plane, then I can't use these 2 vectors to make this third one. Okay, that's enough talking for a Sunday morning. Hopefully you understand it. If not, I think I'll just cry. Have a good day, guys, and yeah, let me know if you need any help. Bye.